So,
Okay.
hi everyone. Hi Lucio. Before we start, a quick introduction. So Lucio is going to talk about connecting the physics of galaxy formation with the cosmic evolution of massive black hole binaries and their gravitational wave signals. And a little bit to Lucio. Lucio got his PhD in astronomy from University of Milano, and then he moved to the US, to the University of Washington to do a postdoc, and then from there back to Europe, to Switzerland, where he held different positions until after some time he became a professor at the University of Zurich, where he is still today. And today he's the deputy director of the Center for Theoretical Astrophysics and Cosmology of the University of Zurich. And Lucio has worked on many different fields, but like the common thing is he cares a lot, let's say, about the structure formation at evolution at different scales. This can be like small scales, would be like small scales in astrophysical manner, like planetary formation and so on, but also large scales like supermassive black holes that is part of his talk today. And predominantly, he looks for the understanding the hydrodynamics with self-gravity. So let's welcome Lucio. Lucio, feel free to take over and enjoy the talk.
Thank you very much, Alejandro, for the very nice and extensive introduction. It's a pleasure to give a talk here in this context. And yeah, as you say, and the title also spells it clearly, I will try to guide you through a journey that attempts to connect the understanding or the attempt to understand the evolution of black hole binaries, in particular the massive black hole binaries that weigh millions of solar masses or even more inside galaxies, to the general context of structure formation and in particular galaxy formation. And the reason why I'd like to spin the talk in this direction is, well, first of all, because I work on different areas and I like to find connections, but also because more in general, in order to really make predictions that are useful for the next generation of gravitational wave experiments, including the upcoming LISA, we really need to understand how to map the evolution of galaxies into the evolution of black holes. And that is really the journey that needs us to take up to the merger stage that will release gravitational waves. So it's a collective effort that with my group in Zurich and many other collaborators, we have been taking over in the past years. And let me just start with a general introduction. I'm sure many of you are already familiar with our current cosmological paradigm, but just in case, because that sets the stage, I'd like to remind you that the current dominant cosmology is a cosmology in which everything happens as a result of two major ingredients: dark energy, or better, the cosmological constant, which determines the acceleration of the universe and constitutes most of the contribution to the energy density of the universe, and dark matter, which in the current understanding is made of collisionless particles. It's called cold dark matter because these particles don't interact through any of the interactions known except for gravity, or better, they might have a very, very weak form of weak interaction, but this is completely negligible. And normally, when you model this type of particles, you just include the effect of gravity. And because gravity is the dominant force, that gives rise to a particular pattern in the formation of structures, such that dark matter clumps due to gravitational instability, first on smaller scales, because of the way, the nature, the gravity works. It attracts first things that are close by, so then you form small halos which grow by attracting dark matter on larger scales, and this leads to larger and larger structures. And eventually, when your dark matter halo is large enough to hold on the rest of the matter and form a condensation of dissipative matter, so baryons, the ordinary matter, that's when you form the first stars and first galaxies. This is happening, we think, around redshift 30. That's a very short time. We are talking about tens of millions of years after the Big Bang, so very, very short. And that's where structure formation begins to be interesting, because you have, from this point onward, the formation of luminous matter, and therefore galaxies. Now, because the gravitational instability of dark matter begins at smaller scales, then we say the structure formation in this cold dark matter model proceeds hierarchically. And in fact, if you look at the history of a single dark matter halo, you trace it from the final time, let's say the present time, redshift 0, backward up to the point where it first formed, what you will see is exactly the plot on the right. This is called merger tree. So it goes from low redshift at the bottom to high redshift at the top. And you see that as you go to higher redshift, you have many, many branches. These branches are the individual smaller halos that come together by gravity to form the final larger halo at low redshift. This is how we think that all galaxies have formed inside halos, really from bottom up. And on the background, you see one of the largest simulations that has been run so far of the clumping and evolution of dark matter halos in the universe is a Euclid flagship simulation that was run by team members in our institute a few years ago, and is basically the reference simulation that the Euclid mission will use to map galaxies to dark matter halos. Now, once baryons are able to cool and collapse inside dark matter halos, because they have, at least we think that they have, from the very beginning, some angular momentum. This is due to the fact that matter is distributed inhomogeneously in the universe, and therefore there are torques that arise that give rise to angular momentum. So the baryons then will collapse and form a rotating disk because of conservation of angular momentum. This is the basic idea of galaxy formation in cold dark matter. Rotating disk forming inside cold dark matter halos. It goes back to the seminal work of White and Rees in 1978. When this first begins, after the first stars form, matter is neutral, but then eventually, after redshift 10, so we are talking about roughly half a billion years after the Big Bang, then enough galaxies form, they produce enough photons, enough ionizing photons, that matter begins to be reionized, and then you enter the so-called reionization epoch, which is for the first time now directly accessible with observations done by JWST. So all this knowledge that we have accumulated about the underlying dark matter model and the standard cosmology that is basically the consequence of general relativity in an expanding universe is encapsulated in the way we model galaxy formation inside numerical simulations nowadays. And I would say since about 20 to 25 years, this field has grown to the point where we can now predict many properties of galaxies. Simulations like the one that I just played, the movie that I just played, can be used to compare with a suite of observations of galaxies at low redshift as well as a high redshift. And we try then to convince ourselves that we understand at least the basics of how galaxies are forming. But if you look at the process of galaxy formation at a bit deeper level, you realize immediately that it's extremely complex, and you wonder whether we would be ever able to really understand everything fully. You have this dark matter background, which is relatively simple because it evolves through gravity. But then as baryons cool and start to form galaxies, there's a lot of things that can happen and complicate the picture. Stars form, and as they form, they also emit radiation. That's the same radiation that reionizes the universe. But even inside galaxies, this radiation will change the thermodynamics of the interstellar medium, and therefore will affect the next generation of star formation. And then if eventually black holes arise by whatever mechanism, I'm not going to talk about formation of black holes in the early universe, but we know that they exist today. So they formed and they grew, some to very large sizes, even 10 to the 10 million, 10 to the 10 solar masses, some of the largest ones. They will also affect the galaxy by releasing energy after accreting matter in the form of feedback through jets, through radiative feedback, and therefore there's a cycle that connects star formation, black hole growth, back to the galaxy where the stars and the black holes are forming. And this cycle is very complicated to understand. It's a cycle of energy and also a dynamical cycle where objects exchange angular momentum and structure evolves. So it's a multi-scale, multi-physics challenge. And the first thing that we have been doing in the last 10 to 15 years in this community of galaxy formation has been to compare not with the detailed observations inside galaxies, but with the global observations of the galaxy population. And this has been quite successful. I mean, today we can claim that most groups that run simulations with different codes, with different prescriptions for all the processes that partake to the cycle that I was just describing before, they more or less obtain reasonable results when it comes to global properties of galaxies. Here I'm showing plots and graphics that are taken from a recent review by Crane and van der Voort on annual reviews. And you can see, for example, here on the left side, the luminosity function of galaxies at low redshift. There are different simulations, Eagle, Simba, Firebox, and so on, overplotted with different colored lines on the data, which are the dots, open and field dots from two different surveys, Gamma and the latest SDSS. And you see that, yeah, there are some variations, but overall, the results are all in the ballpark. They are reasonable within factors of a few in reproducing the luminosity function of galaxies. The same for size of galaxies. You can see on the right the size versus stellar mass relation for two of the most common large simulations that people use to do this analysis, Illustris TNG and Higgle. And you see again the comparison with data is relatively good. You can also look at the evolution of the star formation rate per unit volume over time by taking big samples of galaxies, the biggest that you have. Even that you see in the bottom right plot compares relatively well with predictions of many simulations. And so sometimes the community is tempted to claim success of the overall picture of cold dark matter and galaxy formation inside cold dark matter halos. But in reality, I think we are still far from a full understanding, because when you start looking in detail, for example, at the structure of galaxies, then surprises come. Models and different types of simulations with different prescriptions for the physical processes that govern the evolution of baryons give different answers. So these are detailed aspects of galaxy formation that are still not really understood. And here you see an example. It's a recent work by a former postdoc in my group, Hindra Gensier. She ran different high-resolution simulations of galaxies that are all similar to our Milky Way in mass. And she ran them with different codes and different prescriptions for the star formation and feedback of stars. You see the 3 rows show 3 different samples of these simulations. And it shows the cold neutral medium, which is very abundant in galactic disks. And you can see that the 3 rows show very different morphology of the cold neutral medium. They are systematically different. So each simulation type gives consistent results within itself, but it's different from the other simulation types. And in principle, they should instead give a similar answer if the physics is really robust. So in order to reproduce observations like the one on the right from the H1 survey, the cold neutral hydrogen survey called FINGS, which is a few years old, but is still kind of the state of the art, it's still a long way to go. So there are still many things that we don't really understand about the details of galaxy formation below the scale of an individual galactic disk, so inside the galactic disk. And so today, I think that the situation is getting quite interesting, because we may be at the verge of a big change in computational cosmology, because even with increasing computational power, we might be really close to the limit of what we can do with the way we are modeling things in simulations at the moment. Here, I'm showing you a nice overview of the different simulations that are currently state-of-the-art in terms of either mass resolution or sample size. How large is the volume that they can model? Of course, the more resolution you have, the smaller is the volume that you can model, because it's forcing more resolution elements. And you can see that if you go to very high resolution, the top left of the plot, you are simulating only few megaparsecs. And if you go to very large volumes, hundreds of megaparsecs, the bottom right of the plot, you are simulating galaxies as a point, because each particle in the galaxy weighs 10 to the 8 solar masses or 10 to the 7 solar masses, which is already a significant fraction of the mass of the galaxy. So we are kind of at a turning point where we are asking, what can we do to have much higher resolution and also have large volumes? Well, I think the answer that I would give, and also other people in the field now are starting to lean in that way, is that we need to use a combination of machine learning, AI techniques, and conventional simulations. We cannot do everything with conventional simulations that try to solve directly the equations, because computationally this is too expensive, even with the advent of the exascale supercomputers. But let me just digress a bit away from this general context, and let me go more in the heart of the matter that I want to discuss today. So provided that you have a decent, not complete, as we said, but decent understanding of galaxy formation and evolution, what can we say about the evolution of black holes, big black holes at the center of galaxies, millions of solar masses or larger, that have already grown somehow, and we want to understand how they can pair, form a binary, and merge, because that's really the goal of experiments like LISA, to detect the gravitational waves emitted by massive black hole binaries. Now, the emission of gravitational waves begins to take over the dynamics when the two black holes are already very close at milliparsec separations, but initially they might be in two separate galaxies which are about to merge. And so the story of these two black holes will start when they are even more than tens of kiloparsecs away. Eventually they have to reach the stage where gravitational wave emissions will take over and lead them to coalesce. And today we don't even know if black hole binaries exist. We know that there are dual AGNs, so accreting black holes separated by kiloparsecs in two different galaxies, like in the nice picture that you see in the bottom right. We know that there are candidates of black hole binaries, but they are only candidates, like OJ287. There are many ways to explain variability in spectra other than binaries. There are properties of accretion disks that can also be variable. So at the moment, we have no strong evidence. We have only some tentative evidence that black hole binaries exist. So ultimately, LISA and gravitational wave experiments in general will tell us about black hole binaries and about the merger rate. But we want to make some predictions before that. So here you see the well-known, for many of you, I'm sure, LISA sensitivity curve, and you see the tracks of examples of black hole binaries with different masses, from the lowest that LISA can track in its band, a few times 10 to the 4 solar masses, to the largest that approach 10 to the 7. The lowest must, of course, stay longer in the band because they span a large range of frequencies up to merger. And the very massive ones, instead, they evolve very rapidly in days to months, and then they merge. And all of these black holes will evolve in a matter background. This is something that I will emphasize a lot also at the end of my talk. So the matter background will be present almost all the way up to merger. And I'm going to be back on this topic later on. But for now, let me start with the beginning. So as I said, everything starts with two galaxies, pairs of galaxies with black holes at their center that interact. And because their disks can tidally distort themselves and begin to attract themselves, eventually the two galaxies start to come closer and closer. They undergo a few passages, like in this movie taken from one of our older simulations, and then eventually they will merge. At the center of this simulation, you see these two bright dots. These are models of accreting black holes. So we have essentially point particles that can accrete matter and release energy based on simple assumptions like emitting luminosity close to the Eddington limit. And then you form a single galaxy with eventually a binary of two black holes, and you want to understand how the dynamics of this binary evolves until gravitational wave emission stage. It's actually a long and complicated journey. We just saw the very first part, the so-called stage one, that takes the pair, because they are not yet bound at this scale, to about kiloparsecs separation. Then once they are in the merger remnant, they have to shrink further by some interaction with the matter background. I will describe more about that, but it's an interaction with the gas, interstellar medium, essentially, with the stars and also with the dark matter. And if this interaction is efficient at extracting energy and angular momentum from the pair of black holes, they might get to parsec scales. And when they get to parsec scales, if they are around million solar masses, they will form a true binary. They will be bound. But then, it's still very far from the milliparsec stage of gravitational wave emission. So you have to cover from parsecs to milliparsecs. And that's another important stage, which, is, if you want, governed by different processes. One is the hardening due to stellar encounters with the binary. But there's also the interaction with the interstellar medium again, like at the larger scale. We don't know exactly what is most important. They're probably playing all a role. And eventually, once you reach milliparsecs, everything becomes simple because it's gravitational waves that take over the residual orbital energy. But in detail, these processes that can shrink the binary from parsecs to milliparsecs are many. And even from hundreds of kiloparsecs to parsecs, the largest scale evolution of the pair of black holes, there are many processes that matter. And it's all quite complicated to put together. Here you see an excerpt from the LIS Astrophysics white paper, was published last year, which summarizes the different processes that are relevant to understand the dynamics of pairs and binaries of supermassive black holes. And what I would like to stress is that until now, until recently, there was this simple picture that from tens of kiloparsecs down to parsecs, what really matters is dynamical friction. So the interaction of the black holes with the background treated as a smooth background, as a background with a relatively homogeneous density. This is not the case. As you will see, this is actually very far from correct and makes the picture of dynamical evolution much more complicated to put together and understand. In fact, I think in the last years, there's been a change of perspective. There used to be the so-called last parsec problem. Maybe some of you have heard. I know that some of you have heard because they worked on that in this audience. And with time, it was realized also by people in this audience, Fazil and Peter have done fundamental work on this, that it's not really a problem. That, for example, just with stellar encounters, with three-body encounters between a binary and surrounding stars, you can shrink the binary separation quite efficiently as long as you have a realistic model of the potential of the background galaxy, which is far from isotropic and has various types of orbits which can plunge very close to the binary and maintain an efficient exchange of energy. So this last parsec problem is fair to say is not really a problem anymore. On the other hand, we have realized, unfortunately, that the largest scale from kiloparsecs to parsecs is problematic. Not in the sense that we know that black holes will not be able to form a binary, but in the sense that there is a very complex, and I would say in a sense stochastic behavior, I will show you examples, that makes it very hard to model. One example of this possible last kiloparsec problem is that when the pairs of black holes are in the merger remnant of the galaxy, so after the merger of the two galaxies, they will be delivered at some hundreds of parsecs or kiloparsecs after the merger of the two galaxies. But the merger remnant is complicated. It's not a simple homogeneous object. It is full of substructure. And when you have enough resolution in simulations to resolve this substructure, you need to go to 10 parsecs at least resolution. You start to see that there are different sources of torques that modify the dynamics of the pair of black holes and sometimes suppress the formation of the binary. These torques come from spiral patterns, from bars, from anything that is away from the picture of a smooth background. So this has nothing to do with dynamical friction in a nutshell. And in fact, in these simulations, we were able to measure the effect of dynamical friction versus the effect of the actual torques that the black hole pairs feel in this complex potential of a realistic galaxy. And we found that dynamical friction is subdominant. So here on the right, you see the different components of the torque. The blue lines, which are always higher, are the total torques. And the other lines and the yellow shaded area are different ways of measuring dynamical friction. They're all giving about an order of magnitude less drag than the actual drag measured in the simulation, because most of it is provided by torques that come from global structure in the potential, like spiral patterns or bars. And then the result is that the evolution of the binary black holes is extremely erratic. You can see that in these plots on the left. Some decrease their separation smoothly, some instead, they have a very stochastic evolution of the orbital separation, and this can also increase. Sometimes they are even ejected like for the violet line, one of these black holes is nearly ejected from the disk plane. And then we followed up this problem with an orbit integrator that can look at detailed aspects of the dynamics, assuming a simpler form of the background galaxy, where you have just a disk and a bar potential superimposed to the disk, also dark matter halo around and a stellar bulge. And we found, not surprisingly, that the outcome of the evolution of the black hole pair depends a lot on the initial conditions. So, for example, the phase angle, the initial separation, because depending on the initial conditions, they might evolve smoothly, or they might be trapped in resonances, like in some of the cases that I'm showing you here. For example, in the left column, you see a case where there is an orbit trapping at one of the outer limbal resonances. In that case, the black holes, they will not be able to shrink anymore. They will be trapped unless there is something that destabilizes the resonance. So it's a complicated situation. It's just dynamics. There's no other effect, but it's just the complex dynamics due to a complex potential. And then we tried with Elisa, who was the first author of this paper, Elisa Bortolas, we tried to quantify the effect of the bar itself. It's just one aspect of this complex potential on the evolution of the binary relative to the case where the bar is not present and everything will be just given by the effect of dynamical friction. And you see it is color-coded intensity plot where we show blue is where the bar promotes the shrinking of the binary. So it accelerates the shrinking relative to dynamical friction, and red is where it hinders it relative to dynamical friction. So you have to look at it as a probabilistic plot, essentially, where the color gives you the amplitude of the probability in a certain region of parameter space. And you see that there's a stochastic behavior in general, but there is a trend where there is more red than blue in large portions of parameter space. So the general effect is to reduce the efficiency of shrinking of the binary when a bar is present. So to make the binary evolution slower, essentially. So when you go to real galaxies, and you go not only to present-day galaxies, but also to look at hierarchical galaxies, with JWST now this is becoming a whole field of its own, we find that galaxies at hierarchies have even more complex structure. Not only they have bars and spiral patterns, but they have also something called star-forming clumps. These are extremely massive concentration of stars. They can be larger than a globular cluster, 10 to the 6 to 10 to the 8 solar masses. Some are even 10 to the 9 solar masses, like a small galaxy inside a galaxy. They are ubiquitous in galaxies at redshift 1 and above. JWST is finding them in many galaxies at redshift even as large as 10 or 15, the largest redshift galaxies that have been found. And they comprise a significant fraction of the mass. So now these galaxies really have to be thought of as clumpy objects where the mass is concentrated in lumps rather than distributed. So it's as away as it could be from the idea of a smooth background. Here are examples of recent JWST observations for the hierarchical galaxies. You see these clumps. The galaxies are actually made of a set of big clumps. They are not really smooth objects. And then we tried to model these galaxies since quite a long time because they were discovered more than 15 years ago. And more different simulations now are giving similar results, that you need a very massive disk that fragments due to gravitational instability, the gas disk fragments, and then gives rise to big clumps of gas that then form stars and generate these clumpy objects that we see in these hierarchical galaxies. And although we understand the mechanism of gravitational instability and fragmentation to form the clumps, the question then is, in a galaxy like this, which is common at hierarchy, what would happen to the dynamics of a pair of black holes? That stochastic behavior that I showed you before will become even more pronounced. And here you see examples of black holes evolving these clumpy galaxies. I'm showing you orbital eccentricity and separations. Actually, no, this is only separation, sorry, but you can see from the modulation of the separation of the two black holes, you can get an idea of the eccentricity, which is also reported in the different insets. And the bottom line is you have all possible outcomes. You have black holes that pair and form a binary very quickly, like in the top left plot. It takes only 100 million years to form a binary and get down to the resolution limit of the simulation. But then in the top right, you see the black holes are actually increasing their distance, and one is ejected from the plane. You can see that here in the top, in the bottom right, there's one black dot that goes out of the plane of the galaxy. Because these clumps are massive, they can be as massive as the black holes, and they can scatter them even outward, right? Not only can scatter them inward, but also outward and even out of the disk. So when you are in this complex regime, then the question arises, can we use direct simulations, cosmological simulations which model many, many galaxies and black holes inside them, and can we follow the cascade of events and scales down to the final stage of gravitational wave emission? I can already anticipate, as you probably understood, that my answer is no, we cannot. We have tried, but we now know that it's essentially impossible with the current technology of codes and supercomputers. Here is an example of the status of the field summarized in the Least Astrophysics white paper. These are different simulations that predict merger rates of black holes, trying to encapsulate these processes in cosmological simulations with empirical prescriptions, because they cannot resolve all these different scales. And you see the merger rates with the different curves on different simulations. They are all over the place. There are 2 or more orders of magnitude discrepancies in the merger rates. And we don't even know which one is correct, because there's too much uncertainties on the processes and on the different scales at which these processes are injected. So I would say that we have to step back and change the perspective. And I think really the only way to go beyond the current state is to resort to something that has become, I know, very fashionable. And I have to say, I've been also reluctant to go in this direction for a while, but I'm now realizing that this is sort of inevitable. And maybe it's good that it's inevitable. We need to go and consider a sort of hybridation between direct numerical simulations and AI techniques, machine learning, especially deep learning, to construct emulators that, instead of directly inserting these complex processes in the simulations, they emulate the processes by training the results on smaller scale simulations. Okay, so you have multi-scale effects. You train your deep learning emulator separately on different scales, and then you generate a model where the emulator is integrated into the larger scale simulation. That's a general idea. In order to make it happen, we cannot do it just by ourselves, not just as astrophysicists, but we need to pair this, in this case, us, not the black holes, with a different community, with computer scientists. So this is what we have been doing in the last almost 3 years. We started a project which is called GW Learn. It's a network where astrophysicists, cosmologists, and computer scientists work together to leverage machine learning, especially deep learning, in different aspects of gravitational wave science. One is what I just described, understanding the evolution of black hole pairs and binaries in galaxy formation. And another one is modeling waveforms using AI techniques. So we have people working on all different aspects. I'm, of course, only showing what we are doing in the context of black hole dynamics in galaxy formation. And I can tell you that one of the methods that we are using, which is pretty established, is normalizing flows. And the general idea is to say, look, we have all these complex processes. We don't have a simple descriptor equation, but we can train a model based on detailed simulations of each individual scale. The model trained this way should return a posterior distribution. And the posterior distribution, in order to use a normalizing flow, has to be mapped to a simple distribution via a sequence of diffeomorphism. If the distribution cannot be mapped, the normalizing flow will not work. But luckily for us, usually it works. And at the moment, it seems that it is working. And so what we are doing is really starting from the complex model I showed you before, with the effect of the bar hindering stochastically or promoting stochastically the binary shrinking, and training our normalizing flow neural network on this type of model. And essentially, we construct as a posterior distribution, a conditional distribution on the decay time of the black holes. And the conditions are the parameters, which are 6 parameters: the mass of the black holes, the initial separation, the eccentricity of the orbit, the phase angles, and also the properties of the bar, essentially the mass and the length of the bar, because they measure, in a way, the torque that the bar can impart onto the 2 black holes. The model seems to work because the training has been successful, so the posterior distribution can be fully recovered. We have run so far 400,000 realizations of this model with 6+2 parameters. We like to call it 6+2 because 6 are the parameters of the background dynamical model, which we published in 2022, the Bortolas et al., and 2 are these extra parameters which we vary now, the bar and mass and size. In the original model, they were kept fixed. And then what we do is the 2 parameters that relate to the bar, the mass and the size, after the training part, they are read from a large cosmological volume, the TNG50 simulation, and re-injected so that now they are really covering the range that is realistic for a cosmological simulation. But the training has been done on a larger range. So it's not something that you have to redo because it has already been done on a large enough section of parameter space. And then the machine learning tool, the normalizing flow tool, will return the distribution of the decay time. And this is what you can see in this blue histogram. This is done on a single snapshot. For an example, only here is redshift 1. We could do it at any snapshot and any specific redshift. You can see the distribution that is recovered. It's the distribution of decay times of the binary, if you want binary formation time, from hundreds of kiloparsecs down to the resolution limit of the simulation, which is about half a kiloparsec. And you see that it's quite easy to compare. It's comparing well, it's a reasonable match with predictions from semi-analytical models where they try to inject different processes by hand. Now, the shape is similar, but the orange is the published semi-analytical model from the old way of doing things, using direct modeling in the simulations by some assumptions. The new one is similar in shape, but there are clear differences in the timescales. And we are still in the process of comparing quantitatively, but the bottom line here is we can do this. We are able now to construct this emulator. We will have to do it in time domain. So for now, it's at a given time. It's a single snapshot distribution. The time domain mapping is hard. We are working on it now, but it's conceptually hard. It will require to go to different types of neural networks, like physics-informed neural networks. We will see. But it's promising, and I think it's also very fast because after the training, this is something you can do in 30 seconds. So it's extremely fast to compute. 30 seconds against maybe a full day of computation in a traditional way. Now, let me go to the final topic. I will just spend a few minutes on it because I don't want to run too long. And that's taking us fast forward to very small scales. So provided that we will solve this problem of how to evolve the binary from large separations at kiloparsecs or more scales down to the scale of gravitational wave emission, we can ask another important question. Once you are entering the stage of gravitational wave emission, so let's say you enter the LISA band with a binary of black holes, is the dynamics understandable in vacuum as it's normally assumed? Just as a vacuum problem in GR, you calculate the gravitational wave emission, you calculate the waveforms, and that's it. Or do you have to take into account perturbations by residual matter? The answer is vacuum is not enough. You have to take into account these perturbations. These are the so-called environmental effects that are becoming more studied in the last years. And just to set the stage, the problem that you have here now is the following. You have the 2 black holes already emitting gravitational waves. They are separated by a few tens of gravitational radii. They came there through the interaction with gas, stars, dark matter. We believe that the last stage is governed by the interaction with a circumbinary gas disk, like you see in the simulations that are shown in this slide. But the circumbinary gas disk also is a relatively rich system from the physics point of view. And one of the parameters that is really important is the viscosity of the disk that underlines different aspects of the small scale physics. But in a nutshell, if you have a large viscosity, it means that the gas can flow in to very small separations from large scales. If you have a low viscosity, it means that eventually the gas will not be able to catch up with the binary. So in a low viscosity disk, there will be a radius called the decoupling radius, where the binary will decouple from the matter around it and will just evolve through gravitational wave emission. So essentially like in the standard vacuum picture of gravitational wave emission. But if there is a high viscosity, this gravitational the coupling the coupling radius will be very small. It could be, as in the simulation, as small as 14 gravitational radii. But this binary black hole will be in band, say a million solar mass binary, will be in LISA band at 60, 70, or even 100 RGs. So much earlier than this decoupling radius. It means that there is most of the spiral phase in which you cannot model this system as a vacuum system. You have perturbations by matter. The question is, are these perturbations strong enough to leave effects that are measurable in the waveforms? The first effect which has been studied since quite some time is the dephasing. If you assume that the perturbations to the separation of the black holes induced by torques from the residual gas disk is small, so that it's essentially, you can treat it really as a perturbative effect. So A dot gas much smaller than A dot GW, where A dot GW is the separation change due to gravitational wave emission. Then you can use the stationary phase approximation. So you assume amplitude is not affected, only the phase can change during the spiral phase. And so that the phase shift that might be eventually caused by this residual torque due to the gas around the binary can be expressed in the way you see here as delta psi gas. And then you can make a model of the circumbinary disk around. You can measure the torque as the sum of the gravitational torque between the gas disk and the binary and the accretion torque. So the torque resulting from the fact that as matter accretes, there is angular momentum removed from the gas disk as matter accretes on the two black holes. We are not going to the details of the model, but you can look at it in the paper of Moody Garg, 2022, and also in the follow-up paper in 2024. And what we did is parameterize the effect of the torque with this psi parameter, which gives the amplitude of the torque in an high-dimensional fashion. And if the binary shrinks, psi will be very positive. If it shrinks, the psi will be very negative. If it actually expands, psi will be very positive. So the amplitude of psi and the sign of psi are both mattering. And you can link also this psi parameter to the m dot, the accretion rate of the two black holes, that can be used also to relate these two observations. But I would leave it aside. Just from the theoretical point of view, you want to be able to measure psi because that will give you a magnitude of the effect and the sign of the effect of these torques relative to the emission of gravitational waves in shrinking or expanding the binary. Of course, the gravitational wave will always shrink the binary, but you might have a counter effect due to a positive torque. So Moody has looked at this quite extensively in his 2024 paper with the semi-analytical model with the parameterization of the torque, and has found that the environmental dephasing can be recovered with an error less than 50% using PN waveforms up to 3.5 for circular orbits. If you have eccentric orbits, the error of less than 50% is only reached if you have a very high accretion rate, which is same as saying if the torque due to the gas disk is very strong. So you need to have a lot of matter still around, maybe too much, maybe at the limit of what is likely. But then we said, this is just a qualitative understanding. Let's go a bit more in detail. Let's really do waveform analysis. So again, with 3.5 PN waveforms, here what Moody did is injected environmental circular signals in the left plot. It means injected a waveform for a binary evolving on a circular orbit, but perturbed by the gas disk with a certain amplitude of the psi parameter, with the torque amplitude, for a circular orbit, and then try to see whether it can be fit by a vacuum template on an orbit with a variable eccentricity. In this way, we want to see, can you mask the effect of a phase shift due to gas torques with a variable eccentricity of the vacuum waveform? And the answer, yes, unfortunately, yes. So the two effects are degenerate for quite a large range of parameters. You really have to have a very strong torque. The CG parameter measures the strength of the torque. You really have to be at the upper end of the expected torque strength in order to be able to distinguish it from a vacuum waveform with a high eccentricity. So this is also interesting. You could have these effects that can also be degenerate with other parameters that are sure to be there, like eccentricity of the orbit. And then you can do also the opposite. You can inject an eccentric vacuum signal and see if you can fit it with a circular environmental signal. And again, this is degenerate. It's only when the strength of the torque is very high that you can separate out eccentricity and residual torque. So then the next step, which is the last one that we did in the past year, is the paper is on the archive, it's been submitted before Christmas, is to not do this analysis on a semi-analytical model of binary evolution, but doing it directly in a numerical simulation. So, and here is thanks to Alessia Franchini, who ran some of the first simulations. There are 3D hydro simulations of a circumbinary gas disk around 1 million solar mass black hole binary with dynamics up to 2.5 pn. So the evolution of the orbit is computed using post-newtonian corrections. The fluid is instead still Newtonian. And then we measure this phase shift directly in the simulation instead of modeling it. We really measured, the change in the A dot, in the separation of the black holes, in this model with hydrodynamics and gravitational wave emission, relative to a model where there is only hydrodynamics, so that we could separate out the eventual coupling between the torque due to hydrodynamics to the gas disk and the change in binary semi-major axis and eccentricity due to gravitational waves. This is something we call the coupling between the gravitational wave term and the gas torque term. And this has never been done. It's the first time that this can be done directly in the simulation. Just to be quick on it, we again measured the torque amplitude using the Xi parameter. And what the simulations found was quite interesting. The first thing is that when we compare the gas-only simulation with the full simulation that has gas plus GW emission, and also another control run with only GW, so removing the gas, only GW dynamics in vacuum, we found that there is a residual that is additional to the direct effect of the gas torque. And we model this residual in the way you see below. So we write the A dot, the evolution and separation, as sum now of 3 terms, not just 2. The A dot due to gravitational waves, the A dot due to the gas torque, and the A dot due to a coupling term between the gravitational wave torque, if you want, and the gas torque. This coupling term, just heuristically, like as an ansatz, we model it as the way you see below, as a product of 2 linear terms in A dot GW and A dot gas. So it's the simplest thing that we could think of. And then we have A dot gas with the Xi parameter inside. And in the right plot, you see that we can measure Z, and on the left plot, we can measure Xi. If we don't consider Z, the coupling term, the Xi that we get is the red one, which is larger because, it's like giving more contribution to the torque directly coming from the gas. But in reality, it's a bit from the gas directly and a bit from this coupling term. When you put everything together, you find that overall, the phase shift that we get is on the high side of what the analytical model were predicting. And just to give you a number, for a typical million solar mass black hole, it means that you will have a few cycles. You will lose a few cycles. So you will accelerate the merging by a few cycles relative to the vacuum case. So it's of order a few cycles, but it's based on our analysis should be measurable. Of course, it's just a start because there are many assumptions in the simulation that can be improved. The thermodynamics are relatively simple. There is no MHD, there is no magnetohydrodynamics. So there are several things that can be made more realistic, but it is interesting that these effects are potentially measurable, and they need to be taken into account if they are measurable because they can be degenerate, as I showed, with other parameters of the waveforms like eccentricity. And in another paper that Moody has written with the group of Laura Sbern at Potsdam, it came out that it can also be relevant for test of GR because the degeneracy can exist also with parameters in alternative gravity theories. So I will conclude here so that you have time to ask me questions. I think I showed you essentially 2 aspects of how interesting and complex is also the understanding of black hole binary evolution up to the gravitational wave stage. It's on one end the problem of understanding large scales, which I call the last kiloparsec problem, which I also try to convince you needs a new approach that combines simulations with AI techniques due to the a reasonably large number of scales and processes that need to be taken into account, which before we thought we were not going to do because they were not relevant, but now we understand they are relevant for black hole binaries. So stochasticity can only be tackled in this new hybrid approach, in my way. The other aspect, which is of growing interest, is really the environmental effects on waveforms. And I hope I convince you that residual matter is present until very late in the spiral phase, and these effects can be relevant on one end to have correct models of waveforms, so they would be relevant for making parameter estimation, but also they are interesting because if you can measure the underlying environmental perturbations, you can infer interesting aspects of the astrophysics of galactic nuclei, because it kind of reflects the properties of the residual matter in galactic nuclei. And at the same time, they could be important to avoid the genesis with testing GR deviations. And I will stop here.
Thank you, Lucio, for the very nice talk. So we can start taking questions. Are there any questions for Lucio? Peter?
Yes, thank you, Lucio. Excellent talk, as usual. So I have basically 3 questions connected to your 3 different parts of your talk. So the first one was this last kiloparsec problem. It's very interesting, but in the end, the cosmologist people realize we have some trouble in physics when we describe this kind of cartoon picture, which in the last 10 years, we all like, but everything can be simple, described in some parameters, which is gone from God or whatever. It's very nice, but cosmologist people also realize so easy. And I'm really very excited about this new term, last kiloparsec problem. So we need to solve it, like we did for the last parsec problem. We need to solve the last kiloparsec. Exactly. So this was just a comment. So 2 questions. One about this deep learning stuff. What you did with 6+ parameter, So if I understand correctly, you get some for some of the snapshots for whatever simulation you use this, or doesn't matter which one. So and for this potential, for this one snapshot, you try the different. I like this nice picture when you look in a external potential. You plot the orbits, and we're getting this nice example. So my question is, how complex it would be if we change the potential by time. So the orbital time, if you're looking for one of, you have this picture when you have a 2 black holes orbit, and have this zone when you have this inner resonances and so on. So if the potential changes by time, so if I understand correctly, in this exercise, what you did, the potential was fixed, and you change only the initial parameter. You have a 6 + 2, and the bar may be rotating, so the bar gives some kind of time-dependent potential. But in reality, you understand what the galaxy is growing. So the sizes, masses, everything is changed. So in principle, maybe not so bad the situation, because in reality, you don't get this kind of like an example. You have this very, very sharp range, where the 2 black holes is orbiting. So this, in a reality, it's more complex and it's changing by time. So you don't get such a Lindblad resonance picture in reality. So this is just one kind of things which can help. So this is not inside, and if I understand correctly, this is also not inside in your algorithm of artificial intelligence or deep learning stuff, because you're analyzing only with snapshots. So this maybe help to develop something else when you're adding this time variable potential. So this is what we are doing. Global cluster simulation and orbital simulation. So I'm very excited, and it would be very nice to try, not only for one potential, but this time variable potential, to try the same kind of. I will look on a paper and maybe. The last question is very short. So I am very impressed about this gravitational wave plus environment effect, especially for this last phase. So we always usually think what. Below 100 Schwarzschild radius, nothing happened in the post-newtonian work, and you get a merge. But it's interesting what indeed this gaseous disk can have an effect. So my question, this Gizmo MFM or whatever is the name of this code, is now publicly available, or it's still not?
Okay, so I'll answer the questions in order. Okay, so about the the deep learning approach, yes, you are completely right. I mean, if you want, what we are doing now, which is basically what we left this first paper, will be what I showed is a kind of pilot case, pilot example of what can be done with this type of techniques. We didn't change the model of the potential. We consider only the model that I showed. We did explore, of course, the two parameters of the bar, the mass and the length of the bar. These parameters are free parameters, so they are varied. But the type of potential, like for example, the relative ratio of the mass of the bulge and the mass of the disk, the relative ratio of the mass of the halo and the mass of the disk plus bulge, these things are fixed. So you are right that it's a simple model, and you could also change the relative ratio of the mass of the bar and the mass of the disk, which instead, in our case, has some variation, but it's quite constrained as well.
And also a sizes. You understand that the mass is one parameter, but also a scale radiuses or whatever is also.
Yes. No, so these we change. These we change because we use the scaling. So what we do is, I didn't go into detail, but when we use the galaxies in TNG, in the simulation, the cosmological simulation, what we have to do is we have to find a mapping with each galaxy in a way, right? Because we read all this catalog with all the galaxy properties like disk sizes, disk masses, and so on. We have to map it to some place in the parameter space of our machine learning model, which has surveyed a certain range of parameter space, not everything. And so what we do is we have a way to inject the parameters in a way that is scalable, right? For example, we map a galaxy within a certain mass range, but the disk size is scaled such is always a certain scale of the halo size. So if we have a galaxy that is more massive in halo mass, then the size of the galaxy will be scaled according to how halos and baryonic disk scale, which is something that you can test, is known in simulations. You have roughly some scaling laws between the size of the baryonic component and the size of the halo component. So this part is scalable, and we do it. But for example, we don't use a different potential for the bar. We use the softened needle potential, which was very simple to include in the orbit integrator. But I guess what you were alluding at is that the dynamics can be different in different types of bar potentials or different types of global disk potentials. So this we don't do. So this, yeah. So you could imagine to apply, yeah.
Yes, well, I understand completely. Yes, fine. The last question about the gizmo with PN and gas.
Yes. So this one, Gizmo MFM as a code in general is public, but this change that we did, that Alessia and Alessandro Lupi did, so including the PN corrections, that is not public yet. That's a private version that Alessandro Lupi put together. And this is what we are using now. So that version is still not public. But I think it will. Alessandro is probably going to soon include it in the.
I am just eager to compare our post-newtonian expressions and see what we have the same result or some difference.
Yeah, just for the PN.
Hopefully not. Yeah.
That would be something. If you are interested, we can do this. I'm sure that
just to try the same simple task and looking what we get the same result. I expect what would be the same.
I hope so.
Okay. Yeah, in the post-Newtonian terms, nobody knows. Always can have some trick.
It's possible that, I agree. We did compare with another orbit integrator with PN because we weren't sure as well. So initially we had to do some checks. I agree. Yeah.
Yeah, thank you very much. Thank you.
You're welcome.
Okay, are there other questions? If not, I have myself some questions. First, you are this environmental part. This is for binary black holes that are surrounded by, let's say, relatively high densities of gas, right? Which means these are basically, or I think these are basically AGN galaxies, right? So, but
yes. So you can say yes. You can say yes in the sense that the parameter, for example, in this simulation we use the circumbinary disk that has a mass of 5 solar masses inside, I think, 100 or 200 gravitational radii. So that would map into a typical accretion disk model, not a particularly massive accretion disk, but of course an accretion disk model which is based on modeling AGNs. The accretion disk models are of course based on modeling known AGNs, so known active galactic nuclei, not dormant black holes. I agree.
Okay, so but we also know that not all galaxies are AGN, right? Like maybe 1 out of 100 is an AGN. So I'm just wondering, for how many of the LISA sources that we're going to detect, is this really a problem? Is this just for some particular interesting sources, or is this really relevant for most of them?
So you ask a very important question. So thanks for asking that. I think I can give you only a qualitative answer because we really don't know now. I mean, it's kind of related also to the first part of the talk, right? Because until we understand well how to map, perhaps using this deep learning emulator, the different scales and different processes inside the cosmological simulations, it's hard to make predictions, robust predictions on, say, a redshift 1 or redshift 0.5, how many AGNs I would have for galaxies with black holes that would be in the LISA band, right? This would be the question that we would like to answer. We don't know yet. So with these better models that I think can be developed with the deep learning approach, maybe we will in the future, but for now we don't. But qualitatively, I would say because the typical black holes that are going to be seen by LISA are black holes of 10 to the 5 to 10 to the 7 solar masses. So these black holes are in these galaxies typically, and a large fraction of these galaxies, certainly more than 10%, host active galactic nuclei. Cipher galaxies are very common among these galaxies. So I think that, and this is true even more if you go to higher redshift, although the numbers are not really solid, I think I would expect this to be relevant for a certain significant fraction of LISA sources. Maybe not all of them, but certainly more than 10 or 20%. This is over time, right? Because you have to think about the integrated effect. Many LISA sources will be observed not at low redshift, but at intermediate redshifts, and their AGNs are more abundant because they follow, they're close to this cosmic star formation history plot that I showed at the very beginning. So redshift 1 to 2, there is a peak in AGN activity, star forming activity. So you go to a higher redshift, you will have more of these systems. So I would say certainly more than 10%. But again, solid models don't exist yet. But by the way, even the ones that are not AGNs might have accretion disks that are simply in a state where accretion is very weak, is below the detection limit. It doesn't mean that there is no accretion disk there, right? So it's hard to imagine, in these galaxies in general, which are the typical loss of LISA sources, it's hard to imagine that you don't have an accretion disk because you have an interstellar, in the Milky Way, for example. Of course, the black hole of the Milky Way is not active, but there is gas in the center, and there are even massive stars in the center, so there is matter. I showed this example of circumbinary disk, which is after a merger. But there are other examples of perturbations. There are people studying perturbations even by stars at small separations, essentially stars that are plunging very, very close. So that's more interesting for Peter, of course. So there are other ways to perturb the orbit with matter other than what I just showed. And the last thing that I would say is because it's more important for galaxies that have just had a merger, because that's when you expect the two black holes to still be two black holes and not one black hole. In mergers, you typically increase the inflow rate of gas. And so if you say the galaxies in LISA will be recent mergers, then the mapping between recent mergers and AGNs is even more, not 1-to-1, but you have an even higher fraction of galaxies that would likely be AGNs because they are recent mergers. And the mergers are one well-known way to trigger AGNs.
Okay. I actually have more questions, but I think I will let Reinhard first, and I can ask a question.
Yeah.
Thanks. Hi, Lucio. Nice to see you again here.
Hi.
I don't don't worry. Peter has already asked most of the questions related to our common interest in binary black holes. Or just a bad joke. Maybe let's hope the final kiloparsec problem does not disappear like the final parsec problem. But maybe it's good for gravitational waves. But that was a bad joke. Sorry. I'm more interested in the computational challenges. Yes, you mentioned this machine learning, AI. I'm more still the traditional high performance computing, this 3D hydro with post-newtonian. What's the challenge when you want to go to maximum resolution, massively parallel GPU? I mean, how much time does it need? Could you give us a few words about this, please?
Okay, so right. Let's say if I step back and I say, can I actually tackle the last kiloparsec problem in the standard, the more conventional way with direct simulation? I said no at the beginning, but I didn't elaborate a lot on that. Let me give you an example. So the simulation that I showed that gave us this picture where the black holes are evolving in a stochastic way because of these bars and spiral patterns and so on. These simulations are zooms, so cosmological simulations with resampling. So you go down to 10 parsec scales and you start to resolve all this galaxy substructure in the ISM as well in the stars. And so each of these simulations, took us, we didn't do many, but each of them, so a handful, took us several months. So,
I see.
Yeah, several months per simulation to do one of these things. So clearly, maybe nowadays it could be a bit faster because we did it 3 years ago. So now codes are faster, hardware is better, but still, we're talking about, in the best case, months time scale.
And it's using GPU and a Swiss supercomputer or something, just to get
So those simulations were done with Chang'e and gasoline. Chang'e uses GPUs, but not, it's not fully on GPUs. There are parts of the physics that are not completely.
But kind of 10 or hundreds or thousands of nodes or something like that.
Exactly, but it can be done there. So we have a new code that we are working on now, which is fully on GPUs, which could be better, but that's another parenthesis I would have to open. But let's say, in order to explore parameter space, even if we were going down to a week per simulation, it's still a lot. Because the parameter space is huge, with all these different properties of galaxies, and hierarchical, you have also the clumps and these other types of structures that are also important for the binary and the pairing. So I think it's really, it's going to be, and then you have to do it with different subgrid physics, because if you change the star formation recipe, the feedback, the results will change. We know that. We have done that. We have published papers on that. So it's going to be, even with the best technology that we have now, direct simulations are going to be too expensive to span the parameter space in a reasonable way with the hydrodynamics. I mean, so I think it's, you would need years of calculations to span not even the whole parameter space, but just a decent chunk of it, years of calculations to have a training set that is at the level of what you want to have. But instead, if you do, different scales at a time, right? Each scale can be done faster because you just have a smaller computational volume. You know that better than me. So you can do each scale maybe on, I would say the target would be you do training sets over, maybe, week time scales, but the training sets, but for all the different scales at the same time. And then maybe you construct an emulator that can do the calculation for you on time scales of days rather than on time scales of years.
Thanks.
This is the difference that I have in mind, but I cannot demonstrate that this is possible. It's just, what I can see.
Clear, yes, yeah.
For this emulator I showed, it took 30 seconds to do a calculation that normally would require days.
It's still the question, where is the limit? I mean, there have been papers claiming that the three-body problem can be solved using machine learning and AI. That is how highly non-linear, and I'm just wondering also if you since you just touched this question.
Yes, it's a good question, and I can only tell you that I'm also learning a lot from the computer science colleagues. I don't know. I mean, I don't know what. So they are introducing me to this physics-informed neural networks and
yeah, it seems to work extremely well.
Exactly. It seems to be the way to go. But I mean, I recently talked to someone who is applying that to computational fluid dynamics, so pure computational fluid dynamics. And this person was very enthusiastic, and she showed me very, very exciting results. On the other hand, they cannot do supersonic flows, for example, which of course in astrophysics are very common.
It's common, yes, that's common case. Yeah.
So there are things that maybe they could not be done with the present algorithm we have. Maybe we also have to improve a lot the neural networks. So it's also, I understood even for computer scientists, it's very interesting because it kind of pushes to the limit also their part.
Yes, yeah, absolutely, yes. Thanks.
Yeah, you're welcome.
Okay. Are there any last, let's say, formal questions? Otherwise, I will stop the recording now, and we can maybe